Our next lesson here is going to be on gravity and gravitation. And in this lesson, we're going to look at three things. We're going to look at the four fundamental forces, the forces that all the other forces in the universe basically derive from. We're going to look at the law of universal gravitation, so look specifically at gravity, which is of course the main topic of this lesson. And we're going to look at the Cavendish experiment, the experiment that let us figure out the universal gravitational constant, which is the critical piece in figuring out the magnitude of the gravitational force between two masses. So let's start this off with the four fundamental forces. There are four what we call fundamental forces, or fundamental interactions, another term that's used in nature, that underlie all other forces. And so, when we talk about, say, the frictional force, there is no fundamental frictional force. That frictional force is basically a manifestation of one of these four forces. Primarily, in this case, the electromagnetic force that acts between the electrons of the atoms on the surface of the atom sliding and the surface of the atom. Or we talk about the normal force, which is also mostly an issue of the electromagnetic force. So these four forces basically make up all the other forces. So the four forces that are fundamental in the universe are gravitation or gravity, the electromagnetic force or electromagnetism, the strong nuclear force, and the weak nuclear force. And all other forces are made up of some combination of these four. That's why they're fundamental. These fundamental forces act on types of matter that have different properties and with magnitudes that vary with the distance in different ways. And so when we say they act on different properties, we're basically saying this. Is the electromagnetic force, for example, only acts on charged particles. If you have a particle that's uncharged, the electromagnetic force leaves it alone. The gravitational force, generally you would talk about acting on particles that have mass. And so a particle that doesn't have mass is generally not going to be affected by the gravitational force. We're going to put aside some general relativity part about it warping space for right now, sort of in a classical sense. And so on and so forth. And the second thing is that these forces have different magnitudes that vary with the distance between the two particles that are interacting by this force. And so we're going to look specifically at gravity later on, but the same thing is true with the electromagnetic force, the strong nuclear force, and the weak nuclear force, is that as your distance changes, the magnitude of the force changes. And these fundamental forces, they all act over a distance. They are what are called non-contact forces. The two objects that are acting on each other using these four fundamental forces, any of the four, don't have to be in direct contact. They can be separated by some distance. And so the way that they're going to be exerted then is they're transmitted by particles that we call force carriers. And so these force carrier particles are basically the ones that carry the force from one particle or one object to another object so that that force can be exerted. We're not going to go into a whole lot of detail on that, but I just wanted you to be sort of a little introduced to it, just so you understand a little bit about how these forces actually transmit from one thing to another. So let's move on here. The four fundamental forces. Gravitation is our first one. This is gravity. This is the one that probably of all the four forces that you're most familiar with. Yet despite that, it is the weakest of the four forces. By far, it is the weakest of the four forces. The only reason why we notice it is because we happen to live on top of a planet that has a lot of mass. And so as a result, even though it's very weak, there's a large amount of mass that makes it seem like it's pretty strong to us. Gravity has infinite range. And so gravity acts between any two particles that have mass in the entire universe. So between the computer that's sitting in front of me right now is attracting the Eiffel Tower using gravity. And the Eiffel Tower is attracting the computer that's in front of me. There is a gravitational force between those two, or between the computer that I have in front of me and the center of our galaxy, Sagittarius A star, the name of the black hole that's at the center here. They are exerting a force on each other right now. It may be a very, very small force, but it is a force. So gravity has infinite range. And it acts on all matter that has mass. And so if you have two things that have mass, it will interact between them. That's how gravity works. Gravity is always attractive. There is no case that we know of where you would ever have a repulsive force of gravity. It wouldn't fit with our current model here. So it's never repulsive. Gravity cannot be blocked. And so it's a force that we see we cannot block the particles that carry gravity here. It's believed to be carried by a particle that's called a graviton. Now, we have never discovered a graviton, mostly because the amount of the sensitivity of the detectors that would be needed to detect one is far beyond our technological capability right now. It is believed that it's carried by a graviton, but we have not yet proved that. There are some experiments going on right now called gravity wave detectors, where they're looking at trying to figure out how to discover this as of 2012. But right now, it has not been discovered yet, though we are mostly certain that gravity is carried by these gravitons, and so that's why I put it in here. Second force we've got here is called the electromagnetic force, or electromagnetism. It's probably the second most familiar force to you. It generally appears in the form of electric forces and or magnetic forces. So electric forces are those forces that you talk about, like I have a positive charge and I have a negative charge, and these two are going to attract towards one another, and so that attractive force right there, due to two charges sitting still right here, is an electric force. And so that would be an example of a part of the electromagnetic force. Another would be, say, the force that's exerted between magnets. We talk about magnets having a north pole and a south pole, and if you have another magnet that's over here that has a north pole and a south pole, is that we're going to see a repulsion between that north pole and that north pole as they push away from each other. That force is a form of the electromagnetic force. The electromagnetic force has infinite range. It, once again, is that if I have a charge that's here on Earth and a charge that's in the Andromeda galaxy, they do exert electromagnetic forces on one another, though that force may be so small that it's undetectable. It acts on matter that carries electric charge, or electrical charge. If you have a piece of matter that has no charges in it whatsoever, no electrical charges in it whatsoever, the electromagnetic force leaves it alone. Okay? The electromagnetic force is much stronger than gravity. It is 10 to the 36th power times stronger. And so when we say gravity is the weakest force, we mean it's much, much weaker. A quick way of sort of understanding this is just, take like something like a refrigerator magnet or a small button magnet. Is, you can put it on the refrigerator and it sticks. And so that means that, the electromagnetic force between the refrigerator and the magnet is stronger than the gravitational force between the magnet and the entire Earth. And so that just sort of gives you a little idea of, even something very, very small using electromagnetic force is going to overwhelm the gravitational force of something much, much, much larger, just because of the fact that the gravitational force is so weak compared with the other forces. The electromagnetic force can be either attractive or repulsive. It doesn't have to be one or the other. Remember we said that, opposites attract. We talk about electrical charges. Positives and negatives will attract each other. Positives and positives would repel. So it can go either way. And the electromagnetic force is carried by a particle called a photon. You may recognize that as being basically a particle of light. Light is the way that the electromagnetic force is transmitted from one thing to another. So it's carried by photons. All right, so those are our first two forces. These are your sort of everyday forces in terms of the fundamental force. The ones you would run into and have personal experience with, where you'd recognize you're having experience with it. Our next two are ones that are a little more esoteric. The strong nuclear force, sometimes called the strong interaction, is the strongest of the four forces. So it's 100 times stronger than the electromagnetic force, or 10 to the 38th power times stronger than the gravitational force. Sometimes it's also just called the strong force. They leave out the word nuclear here. But this is the force that holds protons and neutrons together in the nucleus. If you think about it, inside a nucleus, we should have these protons. We'll take a nice simple helium atom here. If I can draw straight. 2 protons, 2 neutrons. If you think about it, those 2 protons should, by the electromagnetic force, want to repel from each other. Is that this one should repel out this way, this one should repel out this way. But why don't they fly apart? Well, the reason why is that there is a much, much strong nuclear force that binds these together and holds them in, that's going to be much more powerful. And so because the fact it's so much more powerful is it holds these protons together, even when the electrical force would make them want to repel apart. And so this is what holds protons and neutrons together in the nucleus. The reason why we don't talk about it normally is because it has an incredibly short range. It's only good for about 10 to the negative 15th meters. That's roughly in the neighborhood of the size of a nucleus. That's why it is the strong nuclear force, because its range is only nucleus size. If you're within that range, then it will hold together things that want to repel. It's strong enough to do that here, but you have to be within the range that's small. If you're outside of that, it's basically useless. It does not act on particles any farther than that. Strong nuclear force acts only on particles that have a certain property that's called color charge. Sometimes you'll hear it referred to color. These are particles that are made, or that are quarks. type of subatomic particle, or particles that are made of quarks, such as protons and neutrons. There are a few other ones here. Electrons do not have color charge, and so the strong nuclear force does not work on electrons. That's why you don't have electrons in the nucleus, among other reasons. So that's the strong nuclear force. It is carried by a particle called a gluon. A little bit of science humor that's in there. You can hear the word glue that's in gluon because it glues the particles in the nuclei together. So that's our strong nuclear force. Our last one is probably the one that is sort of least understood in terms of forces on most people from an everyday basis, which is called the weak nuclear force, or more commonly by scientists, the weak interaction, because it really is more of an interaction than it is a force. It is a force, but it does more just to interact between particles than it does actually think of them in the way of the pushing or pulling like we normally talk about. But the weak nuclear force is the second weakest force. It also acts over very short distances, around the same range as the strong nuclear force, so it's nuclei size, which is why, of course, it's the nuclear force. It causes particles that have a certain property called spin. If you remember from chemistry, is we talked about that in the suborbitals of atoms is that you can have two electrons, each of which has a different spin, a spin up or a spin down. Sometimes instead of saying spin up, scientists will call that a spin of 1/2, positive 1/2. Instead of being spin down, it would be negative 1/2. That's another way of expressing that. If a particle has basically a multiple of either plus 1/2 or minus 1/2 spin, then the weak nuclear force can act on it. It's responsible for certain types of radioactive decay. So, for example, beta decay. And beta decay is that one of the protons or one of the neutrons in an atom turns into a proton, releasing an electron and a particle called a neutrino, which causes the atom to then give off radiation in the form of that electron and to change nuclear to decay into a different isotope. And so this is one of the things the weak nuclear force does. It's carried by particles that are called W bosons and Z bosons. Once again, we're not going to really get to the details of that. But these are the four fundamental forces of the universe. Every other force is some combination of these four. So that's a little intro to your four fundamental forces here. But let's take a look at gravity. Despite being the weakest force, gravity was the very first force to be described mathematically. Isaac Newton, who we've talked about plenty of times before, was the first one to give mathematical definition to gravity in what he called his law of universal gravitation, or what we now call the law of universal gravitation. It says this: every point mass attracts every single other point mass by a force pointing along the line intersecting both points. The force is proportional to the product of the masses, but inversely proportional to the square of the distance between them. So right here we have sort of a diagram of two masses, M1 and M2, sort of look like M&Ms, but in this case assume they're masses here. The force between these two masses, M1 and M2, is said is going to be on a line intersecting both points. And so if we basically found a center of these two, center of mass of these two, the gravitational force is going to be along a line that basically goes between their centers. The force of F2 on F1 will point from F1 to F2. The force of F1 on F2 would be on F2 pointing towards F1. So they're equal and opposite forces, just like we talked about back with Newton's laws of motion. So the next key is here. It is proportional to the product of the masses. And so for this object where you have mass M1 and mass M2, that the gravitational force would be M1 times M2. Okay? And it is inversely proportional to the square of the distance between them. And so if we look at the distance from center to center, and it does have to be center to center, we're going to call that distance R right here, is that it's inversely proportional, which means the R is on the bottom, and so we have this R squared on the bottom here. So that the force, the gravitational force, is equal to G M1 times M2 over R squared. This is our law of universal gravitation. You notice it also says F1 equals F2 because the magnitude is the same. They do it different directions, but the magnitude is the same. Oftentimes, you'll just see us write this out as being F is equal to G M1 M2, that should be an M, M2 over R squared. It's the same formula that we basically have down here. So the gravitational force is equal to big G M1 M2 over R squared. Now notice there's something we have ignored. We've ignored that G that's out there. That G is what is called the universal gravitational constant, or sometimes the gravitational constant. We're going to look at that next. So, get this erased. All right. The universal gravitational constant has been measured to be 6.67 times 10 to the negative 11th units, or newtons, times meters squared divided by kilograms squared. If you use this value of 6.67 times 10 to the negative 11th for g, you will have a force that will come out in newtons if you put your masses in kilograms and your distance between the two centers in meters. And so that's what it is here. This value of g is dependent on the units. If we decided instead of using meters to use feet, then we would have a different value of g. If we wanted to have the force in another unit of force, like pounds or dynes, then we'd have a different value of g as well. So basically the idea behind this universal gravitational constant is it basically puts things from units of kilograms squared per meter squared, which is what you'd get if you just plug the numbers in, into units of newtons, which is our standard unit of force. The first time we discovered this was it was by an experiment done by a scientist named Henry Cavendish in 1798. This was the first time we were able to directly measure g. Now, okay, just a couple of notes here. This universal gravitational constant, for some terminology reasons, is universal gravitational constant is probably one of the more common names. Sometimes it is just called the gravitational constant, but oftentimes it's called just big G. The reason why they call it big G, because it's capital G, we want to distinguish that from little g, which is normally a gravitational acceleration. And so, you know, on Earth, then little g is equal to negative 9.8 meters per second squared. And so big G, though, is this guy right here. So sometimes you'll hear us refer to this as big G as opposed to little g, just a local gravitational acceleration. So just as a quick aside here. But Cavendish in his experiment was actually originally trying to measure the mass of the Earth. That was sort of a question that had been unknown in science for quite some time, and one that people are very, very interested in. Originally, they tried doing things like finding very, very symmetrical mountains. And basically, when they found the mountain that's out here, they basically hung a plumb bob and then looked for it to be slightly angled over to one side, and then looked at the difference to try to figure out what the mass is. But to do that, you had to know the mass of your mountain. They tried to figure it out and had some trouble doing that. They used a mountain in Scotland originally. The French tried it, I think, in South America. Didn't have a whole lot of luck getting very accurate readings. And so Cavendish came along a few decades later and attempted to measure the mass of the Earth basically by using an apparatus where he would be able to measure the gravitational force directly between two masses in a laboratory setting. In a laboratory setting where you can control his variables, make sure there aren't other things that are affecting it. Cavendish also, by the way, is one of the ones that's known for discovery of gases, certain gases, specifically hydrogen gas. By the way, British scientist. So let's take a look at his experiment here. What Cavendish did is he fixed 258 kilogram masses, lead in this case, in place. So while suspending a rod with 2.73 masses on each end to form from a torsion wire in between them. So we can see a little bit of a diagram over here on the right side. We have 258 kilogram masses, one right here, one right here. They are fixed in place, so they would have been on something that holds them in place here. We also then have a rod that is free to turn, that's right in here. On the end of that rod are two other masses. And so these are the 0.73 kilogram masses. Now that rod, as we said, is suspended from a wire called a torsion wire. This torsion wire is one that's basically kept taut. And if you know about the way a wire or a rope works, is that if you twist a rope, it always wants to twist back. And so that force of trying to return back to its original state is called torsion. And so what would happen whenever we set this up is that the gravitational force between the large mass right here and the small mass right here is going to pull the small mass in this way, and the gravitational force on the other side is going to pull the small mass in this way. That's going to cause the whole rod assembly to start to rotate, and so it would start to rotate around in this direction in this case. And so, yeah, so they're showing the final state in this case right here. So it's going to rotate around in that direction. And so as it rotates, then it would twist the wire until eventually it gets to a point where basically the gravitational force between the two masses, the two sets of masses, would equal the torsion in the wire. And he affixed a mirror to the wire up there so he could shine a light at it, and then he could measure exactly how much that angle was. In reality, when he did this, is that he had actually oscillated back and forth a little bit, but either way, he was still able to basically make a measurement of how far the wire had twisted in response to this gravitational force. And so by measuring the twist of the wire, he could find what the torsion force was. And so if he knows how much the wire is pulling back against the force of gravity, then he also knows the force of gravity. They should be equal because eventually they reach equilibrium. And so using that, he was able to find what the gravitational force was. So let's take a look at this. If he knows what the gravitational force is by measuring his torsion, and he knows the mass of his large masses, and he knows the mass of his small masses, and he knows what the distance between their centers is, then he can go ahead and he can solve for his missing piece, which is that gravitational constant. And in doing so, he was able to get a value which was within, I think, like 1.5% of what our modern understanding is of G. And so this is the first time that we were able to actually make a solid measurement on that. And if you know what the value of G is, then in his original experiment, you could find the mass of the Earth. Because you can measure the force between the Earth and an object. You can measure what the mass of your object is. You can measure what the distance is. That's just the radius of the Earth. And so using that, you can find the mass of the Earth. And then with that, we can then find the masses of the other planets and other things along those lines. That's one of the reasons why it was such an important thing. One thing to watch out about is to recall that this radius, this distance between the two masses, is between their two centers. If we basically try to set this up and say, well, the distance between their edges is 2 millimeters or something, or 4 millimeters because it looks more like that. 4 millimeters right here, that would not be our radius. You would have to then add on what the radius of this one is and the radius of this one is to that. Otherwise, you're not going to have that full distance here because we want that total distance, the total between their centers right here, not just the distance between their edges. So this is called the Cavendish experiment. It's sort of well known for that. And so this is how we, found the universal gravitational constant, big G, to be 6.67 times 10 to the negative 11th, and also how we found the mass of the Earth. So let's try to put some of this into play and try working out some problems using our law of universal gravitation. All right. So, first question, what's the gravitational attraction between the International Space Station and the Earth when the ISS is 410 kilometers above the surface? We're told that the mass of the International Space Station is 450,000 kilograms, the mass of the Earth is 5.97 times 10 to the 24th kilograms, and the radius of the Earth is 6371 kilograms. So, starting off with our universal gravitational law of universal gravitation, that the force of gravity is equal to big G times m1 times m2 over the distance between their centers squared. All right, so starting off with that, and we say, all right, we want to know what the gravitational attraction is. That's going to be our force. And so F is equal to big G, which we just said is universal, 6.67 times 10 to the negative 11th, times m1, our first mass. In this case, our first object would be the International Space Station. It's 450,000 kilograms. So 450,000 kilograms times our second object, which is the mass of the Earth. That's 5.97 times 10 to the 24th. 5.97 times 10 to the 24th. It's a 24 kilograms right in there. And we got to divide that whole thing by the radius squared. Now we want our radius to be in meters. Right now is that, right now we have the Earth is right here, the International Space Station is somewhere up there. To find that total distance, we want to go from center to center right up here. And so that means we're going to need both the distance from the center of the Earth to its surface, and then we're going to have to add on to that the distance between the surface to the International Space Station. So the sum of those two is what's going to be our total radius right here. And so adding these up, we know that the height above the surface is 410, plus the radius of the Earth is 6371. And so add those two up, and we should be able to get 6371 our total radius. So R is 6781 kilometers, but we don't want this in kilometers. We want this in meters. So we're going to have to multiply that by 1,000 to get it into meters. And so from that we have, instead of 6781, it'll be 6,781,000 squared meters, or meters squared. So then let's go ahead and multiply this out. 6.67 times 10 to the negative 11th times 450,000 times 5.97 times 10 to the 24th divided by 6781000 squared. And so in doing that, we get a force of 3896953.199 newtons. Looking at significant figures here, 2 right here, 3 right here, 2 right here, 4 right here. We had to add up these right here, the two distances, distance to the tens place, distance to the ones place. So our final distance should be to the tens place right here. So that's 3 sig figs on that one. So our final one's going to be 2 based on what this number is here. And so we would just get 3, that's a 3, 39, 1, 2, 3, 4, 5. So it's 3.9 million, if I'm looking at that right. Yep. So 3.9 million newtons would be the gravitational force of the Earth on the International Space Station, which would also be the force of the International Space Station on the Earth as well. For every force, there's an equal and opposite force, one of Newton's laws here. So that would be an example of how we would use our law of universal gravitation to find our gravitational force. Now, we can also use our law of universal gravitation to find what an acceleration due to gravity is. And the reason why is because we've been defining gravity before the gravitational force before as being the mass times the acceleration due to gravity. And that's still true for this. It's just that that's only going to be one of our masses. It's not the planetary mass. It would be whatever our second mass is. So, so what is the acceleration due to gravity of the Earth on the International Space Station when it's 410 kilometers above the surface? And so this is sort of how quickly is the International Space Station falling as it orbits. That's what we said. An orbit is basically an object that falls as it goes around the planet. Now, looking at this in general, we know that the force of gravity is going to be, by the law of universal gravitation, is big G m1 m2 over r squared. But we also know that the force of gravity is going to be the mass of one of our objects. We're going to say this is m1 for this point, times the acceleration due to gravity, lowercase g, little g. Now, if you look at this, if these are equal, then it means we can do somewhat of a cancellation because there's an m1 on both sides. So we can cancel this out, which tells us that the gravitational acceleration is just equal to g m2 over r squared. And so our big G m2 over r squared. So just a simple rearrangement of that. Let's just figure out what the gravitational acceleration of any body is. All we have to know is what the mass of the body is, of the object of the planet, or whatever you're standing on, or whatever the object is near, and the distance between your center, or the object center, to the center of the planet, or whatever body we're finding the acceleration due to gravity on. So we can find this. So what is the acceleration due to gravity of the Earth on the International Space Station when it's 410 kilometers above the surface? So we're going to sort of do the same thing we did before. This time, though, we can go ahead and start with our gravitational acceleration, which is going to be equal to big G, 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97 times 10 to the negative, 10 to the 24th, not negative 11th, 10 to the 24th, divided by our radius squared. We already figured that out earlier, but I neglected to write it down, so let's go ahead and pull this guy up again. So it will be 410 plus the radius of the Earth, 6371, and so 6781, and so 6781, but we have to get it in meters, so we put this out here. So 6,781,000 squared. And so this should be the acceleration due to gravity at the International Space Station due to the Earth. And so 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th divided by 6781000 squared. And so I get, in this case, the acceleration due to gravity is going to be 8.6598 meters per second squared. Should be the same unit here. Significant figure-wise, we should still be at 2. And so acceleration due to gravity in this case is 8.7 meters per second squared, which, you think about it, is not all that much different than what it is on the surface. On the surface of the Earth, it's just 9.8. And so, going up here, it hasn't actually changed by a huge amount. In setting this problem up here and going up to the International Space Station, is the gravity is actually pretty close. The reason why you're weightless is because you're falling. As that space station orbits around the Earth, is that it's moving sideways fast enough that even though the gravitational force accelerates it inward at 8.7 meters per second squared, it has a sideways component, which is going to make it so that it travels in a curved path as it goes around the planet here. It's falling, and so since everything inside it is falling along with the station, it's sort of like being in a falling elevator, or being on one of those carnival rides where they take you up to the top of the tower and you suddenly get dropped. And so when you drop, is the old trick they tell you not to do is to put a penny, on your leg, and it'll float as you fall here because it's falling along with you. And so the International Space Station falls as it goes around, even though there is a decent gravitational force on it and a decent gravitational acceleration to the Earth, 8.7 meters per second squared. So let's take a look at another case we have here. Once we can get this all erased. One last example problem. All right, so next one up. Planet A has an acceleration due to gravity that's twice as large as planet B, while planet B has a radius 3 times that of planet A. How do the masses of the planets compare? So we're basically looking for the ratio of the masses of these two planets. So let's take a look at this. So planet A, right here, we're told is our smaller planet. There's planet A right here, and then we have our planet B. Planet B has 3 times the radius of planet A. So here's planet B right here. But we're told that planet A has an acceleration due to gravity that's twice as large as planet B. And so, if we're setting this up, we would say, all right, that the planet A has an acceleration due to gravity twice as large as planet B. So acceleration due to gravity for A is equal to twice the acceleration due to gravity of planet B, right there. So we got that. And we said before that planet B has a radius 3 times the planet A. So planet B has a radius, capital P, that is 3 times that of planet A. So we know these two things to be true. And the question is, how do the masses of the planets compare? Well, at first you sort of say, I don't really see any way we can get this, but what we're going to do is we're going to basically set this up in terms of our universal gravitational law. And so we know that the gravitational force on some object on the surface of planet A would be given by this. So let's look at the gravitational force on planet A would be equal to big G times m1, m2, which in this case is going to be ma. It's going to be our planet here, over r squared. And so we're going to say ra squared. And then we also know the same thing is going to be true about planet B. The gravitational force on the surface of planet B is going to be equal to big G times m1 times the mass of planet B over the radius of planet B squared. Now, remember we found before is that our force FB is basically going to be equal to the gravitational force, the gravitational acceleration times m1 right there. And for FA, it's going to be the gravitational acceleration GA, little GA times m1. Whenever we set that up, we can sort of see, okay, we can do some canceling here. m1 cancels off of both sides on both equations. And so we're just left with the gravitational acceleration of A is equal to big G times ma over ra squared. And the gravitational acceleration of B is equal to G mb over r b squared. All right, so we've been able to figure out the gravitational accelerations. But we have a relationship between those two. we know that the gravitational acceleration of A is twice the gravitational acceleration of B. So gravitational acceleration of GA is G times the mass ma over RA squared. But we know that gravitational acceleration GA is equal to twice that of GB, and so this is going to equal to 2 times our other guy over here, the gravitational acceleration of GB, which is G times MB over RB squared. We know those two have to be equal. Now, looking at this, we can do some further canceling because that's going to cancel off our universal gravitational constants. And so we now just have ma over RA squared equals 2mb over RB squared. Now, RA and RB, we have a relationship. We know that RB is equal to 3 times RA. And so we can further, and I'm going to go ahead and write it over here, we could say that, okay, we know the mass ma divided by RA squared is going to be equal to 2 times the mass mb divided by RB squared, but RB is equal to 3RA, and so it's going to turn into 9RA squared because we're squaring 3RA, and so the 3 squared becomes 9, and so 9RA squared. All right, so we know MA over RA squared is equal to 2 times MB over RA squared. And so we're looking for basically our masses. So let's rearrange this to get a ratio. So let's move up the RA, multiply that, or let's move our RAs all to one side. Let's move our masses to the other side here. And so I'm going to get MA on this side. I'm going to divide both sides by MB. So I get an MB on this side right here. I'm going to multiply my RA squared that's on the left up to the top. And so I get 2RA squared divided by 9RA squared. Well, looking at this, you can sort of see our RAs are going to cancel out. So RA cancels out, RA squared gets canceled out here. And so we see the ratio from mass of planet A to mass of planet B is just 2/9. Or in other words, that the mass of planet A is equal to 2/9 of the mass of planet B. And so planet A is considerably, in this case, less massive than planet B is. Yet, it still has an acceleration of gravity that's twice as large, even though it has a smaller mass. The reason why, it's a smaller planet. If we wanted to find the density of these planets, we could do that. Because at least with the relationship, we'd find the ratio of the two densities here because we have their mass. If you wanted to find their volume, it's just going to be it's a sphere for these two. Volume of a sphere is just equal to 4/3 pi r cubed. And so since we have some information about the radius, we could go ahead and plug that in, find the volume. Since we know the ratio of the masses, we know the ratio of the radii of the two planets, then we could then go use that to go ahead and find the density if we wanted to. But these are some examples of how you would do problems using Newton's law of universal gravitation.